us something about the structure of replicable hypothesis testings?
Sector. Hi everyone, can you hear me?
Yes.
Okay, great. Yeah, so I'm Justin. I'm going to be talking about this work on replicability and hypothesis testing. This is joint work with Anas, Miriam, Sham, and Sandeep. Okay, so this is a short talk, but I want to get across a couple points. First, what is this notion of replicability? So replicable algorithms are algorithms which are consistent with high probability over resampling. So they take samples from some distribution, and you want them to answer the same output on different resamples. And then describe sort of briefly what we do in this space. So we provide generic recipes to take sort of distribution testing, upper and lower bounds in the standard model, and turn them into replicable upper and lower bounds with minimal overhead. So to get started, sort of the picture to keep in mind is there's some distribution in the sky. So we'll use the example of a biased coin for a lot of this talk. And there are two scientists who want to conduct some experiments. They want to test something about this ground truth distribution. So they both get some samples from this coin. One scientist determines that the coin is fair, and the other scientist determines that the coin is biased. Okay, so this is maybe not a desirable outcome. You might not have a lot of faith in their procedure if you see that they get samples from the same distribution and come up with a different answer. But this is not a result of necessarily the procedure being correct. In sort of the standard property testing model, the testers can be correct and with high probability that they accept under the null distribution and reject under the alternative hypothesis, or if the distribution is far from having a property, while still being unstable. In particular, if the coin either falls in the accept or reject case, then we have no guarantees on what the algorithm might do. Okay. And so, motivated by these sort of examples, Padvaso, Lay, Tassi, and Sorrell gave a definition of replicability for statistical problems, not just for testing problems, but that's what we'll focus on today. Okay, so I'm going to set up the formal definition, which is given an algorithm A, which takes random input, so it takes data set X, which is a sample from some distribution, and also a random seed R. Okay. And we say that A is row replicable if the following condition holds, which is I'm going to imagine sampling X and then also sampling another data set X prime from the same distribution independently, as well as sampling the random seed R. And I want A when run on X to equal A when run on X prime with high probability, so the probability of 1 minus rho. And importantly, A in these two instances fixes its random seed. Okay. So that's the formal definition. And so if these two scientists can sample and agree on a random seed and then draw their independent samples from the ground truth distribution, then they'll agree with probability 1 minus rho. Okay. So it's the idea here is that the algorithm is consistent with high probability over resampling the data. Cool. So why is this something you might care about? I'm just putting the definition back. So this notion of consistency implies that the algorithm doesn't depend too much on the specific sample set it saw, right? If I give the same answer, even if I resample from the distribution, really my algorithm is more a function of the distribution than it is of the particular sample I've seen. So this is some notion of stability. It also will imply generalization. And it also captures some notion of privacy. I can't depend too much on any individual sample point that I saw. Other benefits of this definition is that it's sufficiently verifiable. It's easy to check that this condition holds, which is not true of some other notions of algorithmic stability. And it has some algorithmic applications actually in the design of local computation algorithms. Okay. So, yeah,
so is consistent defined for a specific distribution? Can like an algorithm be consistent with respect to one distribution but not to the other?
That's a great question. So generally, you could consider both versions, but generally we'll consider the sort of stronger version of replicability where, there's some allowable class of distributions, but even for distributions that, for instance, don't fall in the accept or reject case, sort of for any distribution that sort of fits the schema that we're concerned with, we want the algorithm to be replicable.
Right.
So this is also similar in if you're familiar at all with differentially private testing, you want the tester generally to be private for any distribution, even if you might be assuming correctness only for a specific class of distribution. Right. Okay, so I'm going to describe sort of how you might, what a replicable algorithm looks like. I'm going to stick with this coin example, so I want to reject if the coin has bias less than a half and reject if it's more than a half plus epsilon. So let's first consider sort of the most standard tester, where I'm going to take 1 over epsilon squared samples and compute just the empirical mean of the outcomes I see. And so I've drawn sort of confidence intervals of with roughly order epsilon around the empirical means from the 2 different experiments, or 2 different sample sets. And then I'll just place a threshold at a half plus epsilon over 2 and accept if the empirical mean is less than this threshold and reject if it's above this threshold. So this is sort of the standard tester. And the problem is that if the true bias is right at this threshold, then with constant probability, my 2 different experiments will land on either side of the threshold, and I'll get inconsistent answers. Okay, so this is sort of an easy explanation of how a standard algorithm can fail to be replicable. Okay, so how do you enforce consistency? This is sort of a basic tool for a building block for replicable algorithms. And that was introduced in the paper that introduced this notion. So I'm going to blow up the number of samples I take by a log 1 over rho squared factor. And I'm going to do the same thing. I'll take the empirical mean, but this time my confidence interval is going to be smaller, so it'll be with epsilon rho with high probability, with probability 1 minus rho. And then instead of picking a fixed threshold halfway in between the accept and reject cases, I'm going to pick a random threshold in some sort of range. And so what can go right or go wrong? Again, if the random threshold lies sort of right around where the true bias is, I can have a problem in that I can land on either side of it. But if the random threshold sort of falls completely outside of, both my confidence intervals are to the left or to the right of the random threshold, then I should be happy, okay? Because probability 1 minus rho, under this resampling, the 2 scientists will agree. Okay, and so what's the probability of this occurring? Well, these confidence intervals have width rho times epsilon. I'm choosing the random threshold from an overall interval of size epsilon, so it only happens with probability of rho that I'm unlucky and my random threshold lies, intersects these confidence intervals. So that's how you can achieve a replicable algorithm. And in fact, if you allow yourself to take samples adaptively, then the expected number of samples you can take is less than this 1 over rho squared factor. And the idea here is first sample the random threshold, then take a few number of samples. You have a big confidence interval. Right now it intersects with the random threshold, so I'm going to take more samples, get a more refined confidence interval. Now it's completely to one side of the random threshold, and I'm confident if I resampled, I'd still be on the other side. So that's sort of the basic building block of replicable testers is this random threshold approach. So prior work has studied replicability in several learning problems, in clustering and statistics. It's also been observed that replicable coin testing, it's not just like a nice example problem, it gives you sort of black box results for any sort of testing problem, and that you can just view the success probability of a non-replicable algorithm as the bias of a coin that you want to test. So this gives us quadratic or linear blow up in 1 over rho, depending on if you take the samples deterministically or adaptively. And we were really inspired by a prior work by Liu and Yi on replicable uniformity testing, which gave a result that showed that even deterministically you can actually do better than this 1 over rho squared blow up. So the normal number of samples you need for uniformity testing is square root of n over epsilon squared, and they only incur an extra 1 over rho factor, as long as n is large. They also gave a lower bound that matches up to logarithmic factors, but only against algorithms which are invariant or relabelings of the underlying distribution. Now in the standard model, it's well known that for uniformity testing or any symmetric property, it suffices to just prove lower bounds against these label invariant algorithms, as any algorithm can be turned into a label invariant algorithm and no cost to its performance. But this was not known for replicable algorithms. Maybe some replicable algorithm is doing something really strange with the labels in order to be replicable. There's also connections between replicability and differential privacy and other forms of stability, and some concurrent work of Ilias and other co-authors that has some of the same results in our paper. So let me go over what we're able to show. So our first contribution is to investigate structural properties of replicable algorithms. So we show that this connection that suffices to just look at label invariant testers for symmetric properties in the standard model also holds for replicable algorithms, and actually much more. We essentially show that any replicable tester, you can turn it into a tester that uses this random threshold approach. So that is sort of the canonical way of making a tester replicable. We also show a sort of general technique to prove lower bounds via chaining. So in sort of standard distribution testing, you have some family of hard distributions in the reject and accept case. Since a lot of the interesting stuff for replicability is happening in between, you have to sort of have some continuum of hard instances between accept and reject. And finally, we show a sort of general framework for turning existing testers into replicable testers. So any tester which essentially computes some statistic, shows there's a gap in expectations in the accept and reject case, and bounds the variance. We have sort of a black box way you can turn that into a replicable tester that minimizes the replicable overhead. And from these results, we get improved bounds for coin testing, uniformity and identity testing, closeness testing, testing of Gaussian means in high dimensions, and also some non-testing problems, so some distribution selection problem, which we achieve through sort of iterative testing. Okay, so maybe just towards the end, I wanted to mention something about these structural results. So we show the sort of following properties, that if you give me any replicable tester A, I can construct another replicable tester that's what's called a canonical tester that has the same correctness parameters, but also some additional structural properties. So these were not known before, but they're sort of things you might expect out of a tester. So order invariance. B has the same behavior as canonical tester, regardless of the order in which the samples are received. Label invariance. So if the property doesn't depend on the labels, then B has the same behavior regardless of a relabeling of the elements. And it will actually show a slightly stronger form of replicability holds. That's I won't get into due to time. And then more generally, that sufficient statistics in the non-replicable setting are also sufficient statistics for the replicable setting. So how do we achieve this? So one attempt is sort of to average the behavior of A across, let's say for the sample order result, across different sample order permutations. But it's sort of delicate. It's hard to argue that the algorithm isn't using some sort of useless properties of the order of the samples in order to achieve replicability. So the way we sort of show all these results is via an intermediate lemma, which is showing some other structural property, which is that there always exists some canonical tester that computes a deterministic function of the samples, and then samples a random threshold. Let's say the deterministic function lies into the interval 0, 1. I'll sample a random threshold in this interval, and then do the, just help it accept if the statistic lies below this threshold and reject otherwise. So the sort of example I showed for coin testing, which is an upper bound, is actually sort of the structure. You can view it as the structure of any replicable tester. So you can view some statistic and randomly threshold it. So I think that's about as much time as I have here, but I'm happy to talk about any of the other results offline.
So I have time for one question when the new speaker will.
Oh, that's a problem. I'm the next speaker, but they have a question. I hope it's short. Let's say I try to canonize every, a non-replicable algorithm, okay? Just use a blow up of 1 over rho squared and then sample a subset of the original number of samples. Isn't it always be rho replicable?
Sorry, what do you mean by sample?
Let's say I have a non-replicable sampler with Q samples, okay? And then I make a canonized algorithm. I just take Q over rho squared samples, and then the verifier just take Q of these Q over rho squared samples, and then makes the same decision as the original algorithm. Isn't it just makes?
No.
Isn't it just too easy? That's what I ask.
Yeah. So I mean, this is not possible. I mean, the bounds are the relationships are tight, so it's not possible. And so the reason why is that you actually are solving a stronger problem. You're solving. I mean, I don't really have time to go into this. Maybe offline, but
Yes.
replicability is somewhere between tolerant testing and normal testing. It's a harder problem you're solving. You can't just
Let's take this question offline and let's say just in case.